queued up, which is also totally awesome. But before we get going, is there how's my sound? Let me get my headphones on here. How's my sound and my my video look for everybody? Sound is good. Thank you, Kyle. Appreciate that. How does the video look? I'm gonna see if I can make sure that people can see. Okay, we got some good sound. More echo with the earbuds on, he says. So, oh, you know what? Let me try if I can fix that. Okay. Sweet. Okay, so while we're giving people a little bit of time to come in, I'll answer a few questions. Gakas, Ghakas, asked a question and says, calcium-free cement, such as magnesium oxide cement, would it be considered the future cement, applying the concept for green building materials? So I think magnesium oxide cement's a very interesting cement. I've done some testing with it. I think it's got a lot of stuff to get figured out. I think there's a lot of potential, but one of the big challenges with that cement is you have to have a huge amount of raw material, magnesium raw material. And right now the earth doesn't have a reliable supply of magnesium oxide to produce a large volume of that cement to meet the demand that we currently have in our concrete industry. So I think it's cool. I think it could be used for some things, but I'm not sure it's going to be used widespread. So we got some other people coming in. We'll give you about a couple more minutes or so. So I'll give you, oh, look at that. We got some thumbs up and everything. So, hey, I appreciate everybody. Hey, and I'm Texas Barnuminiums. Glad you guys are here. I appreciate it. So just so everybody knows, there's going to be a lot of students on the call, and some of them are going to be having questions on possibly their homework or maybe a couple other things to do with the class that I'm actually teaching right now. We've had to move online, so everything we're doing is online, and so I want to make sure I get their questions answered, but I want to answer your questions as well. I don't over the first hour or so, I'm going to be focusing on their stuff. Maybe I won't go an entire hour. We'll just kind of see how this goes. I'll be focusing on some of their questions, but I'm going to also have some breaks where I answer your other questions as well. So I really want everyone to be engaged, and I really appreciate you for being here. When you type your question out, if you could do your best to make it as thorough a question as possible, like a beginning, middle, and end. Just take a few seconds to make sure that question is extremely clear, because if it's not clear, then I'm probably not going to talk about it. Also, if for some reason you're one of my students and you did not get your question answered, then I would recommend you email me about it. We want to make sure that you're taken care of, and there's going to be videos that you're watching for this class on YouTube, just like I sent you an email about it. But let's get started. Man, thank you for all the sweet comments I'm getting from people. I really appreciate it, and I love concrete too. Ronith, I thanks for saying that. Yeah. So before I get on to these T-beam questions and slab questions, I'll answer this one. It says, hey, Tyler, what kind of concrete structures or elements would you feel safe to use stainless steel rebar closest to the surface and normal steel rebar further inside? So, Eric, I think it depends what you want to do. If you were going to be doing the slab, or that where you could put something like stainless steel on the outside, but then have a few other rebar in the center. I think that would work out great. I think that's expensive. I think that's a lot of people aren't going to want to do that, but you could do something like that. Also, if you put rebar in the center of a slab, it doesn't really add a lot to strength. And so there's some people that may get concerned about that. But I think it's a great idea, and there's a lot of people experimenting with that. So I'd say thumbs up and keep thinking about that. Awesome. So now let's get to our T-beam questions and slab questions. Let's see here what we got so far. From T-beam design, Kyle says, here we go. Says, is there a flange thickness requirement or guideline? So in my class right now, we're actually working on slabs, T-beams, and double reinforced beams. They have a homework due on Wednesday. So that might be why you might see some more questions about that. They also asked me a few questions over the weekend. I tried to answer them. There was like a lot of them. And that's good. That's exciting. That's what we want. We want questions. But when what we're talking about in T-beam design is if I have a beam that, well, usually when T-beam, and this is a whole lead into some of the stuff I wanted to talk about today. If we were going to do like an elevated slab, like something in the air, one way to do it would be to make a huge, very thick slab. But that's not very economic. As you start to load that slab, it would crack. It would have to have lots of steel. This doesn't make sense. If you actually look all around your life, people have done these things on ships, a lot of plastic structures, a lot of other things like that. They use things called stiffeners. So they'll put a stiffener on that item, and then they'll go further, and then they'll put another stiffener on it, and then they'll go further, and then they'll put another stiffener on it. Now, when we make our elevated slabs, that's actually, we're doing the exact same thing. And we call this a T-beam. This thing is called a T-beam, because there's some section over here that we stop at, all right? That's the effective width, the B effective, right? That's the effective width of the beam. And then that is like a T, and it acts like a beam. And if it's loaded, it's going to have steel that they would put in the bottom. Remember, this is elevated. This is stuff that's in the air. We do the same type of things with footers on the ground, same type of thing. And so that's why we have these ribs. Now, one cool thing about that is that when it's loaded, if it's going to crack, and we know kind of the region it's going to crack at, it's going to crack towards the bottom. So let's say this region right here may crack. If one cool thing about that is if that is the cracked region, that's a small part of our structure. As opposed to if we do this, if we made instead of these rib sections, if we made the entire section thick, if it cracks, the entire thing would be cracked. Look at all that crack, all that would be cracked. And so what we can do is we can actually use less material with this. We can get the same capacity, yes, the same capacity as something like this. And that's why we have these rib sections. They're more efficient. They're more effective, right? That's what it's all about. But Kyle's question was, for T-beam design, is there a flange, right? Flange thickness requirement or guideline. So he's talking about this flange. That is the flange. That is the thickness of the flange. And that is actually the thickness of our slab. The slab that we have elevated, the slab that we have in the air. And he says, what is that? Well, the minimum thickness for a slab is 6 inches. That's elevated slab, not slab on ground. Okay, minimum thickness on slab on ground is 4, but 4 inches is really thin. But for elevated slab, it's 6 inches, and that's mainly because of fire reasons, and also because of point loads and also deflections. Right, so that's that question there. Hey Ted, thank you for the comment, man. I'm glad you've gotten some stuff out of the talk, and I'll be in Utah in the fall, so maybe we can talk then. Here's a question: is there external and extreme exposure cover thickness for slabs? So thanks, Mo. So if you have a slab like this, most of the time when we talk about cover, it's actually strange for a slab. For internal slabs, and this is for elevated slabs, but for internal slabs, our cover is 3/4 of an inch. Okay, and if it's an external slab, so outside external, then our cover is 2 inches. And if you're in an extreme environment where you're really worried about that steel, you really want to protect the steel with cover, then in extreme environments, then you would go up to 3. Awesome. Let's keep moving ahead. So lots of echo with the sound. How about other people doing with the sound? We were doing, all of a sudden lots of echo. I don't know what happened. Let's see. I think smart concrete would be a good idea. Someone just said that was echoing a lot. Well, let's see what I can do about that. That's strange because it wasn't echoing before, right? And now it is. Let's see. Yeah, I think. Oh, an echo and I lean forward. Okay, well, I'll try not to lean forward anymore. How's that? Yeah. Awesome. Let's see what I can do. I can actually, maybe hide this. The sound goes in and out. Being echoey, but it's good now. All right. So I think I just need to stay away, and I will play with the echo stuff coming up a little bit. Let's see, what do we got? I think so. Omar asked, why does the concrete crack at early stages without any load? So that's a good question, Omar. So concrete shrinks, and if it's held in place and it tries to shrink, then it's kind of internally loading itself, and that can often cause cracks. That's why one reason we use something called temperature and shrinkage steel. That's kind of the minimum amount of steel that you would put inside of a member, just in case it temperature changes a lot or the shrinkage changes a lot and it's restrained, and then it ends up cracking. That's usually the reason why it does. Okay. Lots of echo comments. Let's see. All right. I don't think how's my echo now? Is it better? Turn your speakers down. I don't even have any speakers on. Let's see. I think they are down all the way. Yeah, they're off. Let's try this. Okay, is that better or worse? Better. Yeah, the earbuds are gone. So they're out, and they say it's better. So thank you. All right. So do we have any other questions that people would like to ask? Any other questions on slabs, doubly reinforced? Some people are saying it's the same, and some people are saying things are worse. So let's see. I'm not sure what to do about the echo. I've got everything turned off. I've got my computer muted. And so I hope it gets better. I could try to turn off. Oh, you know what I could do is I could try to turn that off. Okay, so see if my echo is any better. So Christina asked the question, are we only having one live time a week on Monday mornings and the rest instruction will be posted for videos? I think that's true for now, Christina, but we're going to kind of see how things go. Then we may have some other private times where you can meet and ask me questions, but that's kind of the plan right now. How is my echo now? Is it better? It is better. Have a wider web, stack of rebar. Oh my gosh. Oh my gosh. Let's see here. It changes it. Tell me about the echo. Aha! I think I fixed it. So thank you guys for your help. All right, let's see. Man. Jacob asks, are there going to be example videos with examples worked out? Yeah, of course, Jacob. There will be lots of videos with examples worked out. I have some that are already posted, and there'll be a lot more. Kyle asked, is it better to have a wider web or a stack of rebar and a thinner web? So Kyle, I think you're talking about for T-beams, and I think that's just your choice. It depends on what you have for your structure and what you think can fit from there. There was a question earlier about, let's see, Vindusha, thank you for the question. You said, hey, how much fly ash should we use to prevent oxidation of the reinforcement bars? So typically, if you're using a class F fly ash, you want to use about 20%. That's what most folks use. If you use a class C ash, it really depends on the ash. Some ashes actually hurt your permeability of your concrete, so you have to be careful with those. But usually you can use them at about 20%, and they're about the same as Portland cement. And sometimes they're better. So 20% is a good number. If you increase the number of class C fly ash, then the permeability will go down. And they're usually almost always below with a Portland cement number. So I hope that helps. Awesome. So I'm looking for more questions here. Let's see. All right. So much better. Great. So Julio asked about, how about double reinforcement at T-beams when we have a big load relative to our length? So Julio, I'm not exactly sure what you're asking here. How about double the reinforcement at T-beams when we have a big load relative to our length? I think that just means if you have a lot of load, could you stack rebar inside a T-beam? And the answer is definitely yes. You could use many layers of steel if that's what you needed to on a T-beam to give it your satisfactory strength. That is 100% possible and could be done. Let's see. People are saying my echo fixed. Appreciate that. Yeah, so Rihanna asked me, when double reinforced, when finding D prime, is it ever different than finding the distance of H to normal D? So Rihanna, if you remember, D prime D prime is the distance from, if you have a beam, a typical T-beam, that is the distance from your compression fiber to your compression steel. So that would be this distance, and it would go to the centroid of that steel. That would be, yeah, that would be the distance for D prime if you look at a T-beam. What that's all about. Awesome. Yeah, so I'll ask if I could use something other than YouTube, so I could everyone just from our class, I think, in it. So if you want a private session, we can do that on YouTube. But I think it's helpful. We'll see if we can fill up this hour of time with actual questions. If I can help other people, other places, with other classes, with their homework and their questions, then I want to try to do that as well. Let's see. Man, lots of questions. So I guess I just need to pick one because I'm not seeing any T-beam type questions or double reinforced. So what is your opinion on coarse aggregate absorption and coarse aggregate's ability to resist freeze-thaw problems? So there's certain aggregates that can have freeze-thaw problems. They usually have a certain pore size inside of them, and if you get those and you use them inside your concrete, then once that aggregate gets saturated and freezes, then you can get freeze-thaw damage, and you can have problems with your concrete. So that's something to watch out for. All right, so I am trying to find another question from my class. Is there any questions from my class? Rihanna asked one. She says, yes, but is that distance difference from the reinforcement from the bottom fiber to the tension bar? Yeah, it is. So if I have, let me try to explain that a little bit better. If I have a beam and that beam is being loaded from the top, and if I was to draw the cross section of that beam, let's say that is the cross section, and I have some rebar at the top and I have some rebar at the bottom, and I wanted to find the stuff that's in tension, that's the bottom, that's the T at the bottom, and the C is the material at the top, that's in compression. So the D prime would be the distance from the compression fiber to the centroid of that steel. And the D, the typical D, would be from there to the centroid of the tension steel, something like that. So they are different. They are very, very, very different. And so D would go from compression fiber to the centroid of the tension steel, and D prime would go from compression fiber to the centroid of the compression steel. Hope that makes sense. So now Alex asked, when we have two layers of bars, where do we measure D to? So Alex, if I have two layers of bars down here at the center, we have to go back and think about what is the definition of D. D is the distance from the compression fiber to the centroid of the tension steel. Well, if I have two layers of tension steel, then I need to go halfway in between them, and that is ultimately where my D would end up being, something like that. It would be there if I have two layers. So again, you have to go back to your basic definition. All right. So one question we have here is cross-laminated timber, the concrete of the future. I don't think so. I think that if you go back and look at history, timber has had problems in large buildings because of fire. And I'm still concerned about that cross-laminated timber and how it performs in a fire. Some people will say that it's treated so that it's more fire resistant. One bad thing about that, though, is once it gets hot enough, it starts to outgas, and that gas is actually toxic for the people around them, and it can kill people or not be able to allow them to freely get out of a building. So I think if you look at history, there's been this movement of people start to use timber, and then people start to move away from it, and then people start to move timber, and then people start to move away from it. Now, maybe we can get a big technological breakthrough that'll help make timber possible to be used, but I think that ultimately I'm not convinced that we're not going to move away from it after some large fire events or other concerns. All right, I'm looking for other questions about T-beams or double reinforced or something else. Joe, hey man, thanks a bunch. I was wondering if I could talk about craze cracking on internal slabs on grade applications, specifically what causes it and how to prevent it. So for folks that don't know, if I have a slab that's internally and sometimes this can happen if you don't do a good job curing the surface, or if there's a big temperature shock to the surface of the concrete, then you'll actually get craze cracking. Sometimes it's caused by plastic shrinkage cracking. That's with high amounts of wind or very low relative humidity, but that's not always the case. Sometimes it's just a quick temperature change or a quick shock to that surface. So you want to cure your concrete. You want to protect that surface. You want to, as soon as the bleed water starts to go away, you want to try to keep that wet. Curing compounds are okay. They're better than nothing, but keeping that water wet with some kind of mist, some kind of wet cure is the best. Now remember, I'm not saying work that water in the surface. I'm saying wait until that water has evaporated and is no longer there anymore. And then you want to keep that water on the surface wet. And that's what I see causes craze cracking the most. And so maybe hopefully that can help. So I'm looking for more double reinforced questions, etc. Let's see. Andrew just asked, of course, as far as coarse aggregates, do I have a maximum percent absorption? So actually, Andrew, I've found, and I've done a lot of testing on this, that it's not about maximum percentage absorption when it comes to coarse aggregates. See, like these aggregates all have voids inside of them, and that it's not about the total amount. You can't just rule them out by that, by actual total amount. It's all about the pore size distribution inside the aggregate, and whether during freezing and thawing events, if that causes some damage to the concrete. So you really have to do like a freeze thaw test on the concrete. That's the best way to know, or look at historic performance of the concrete aggregate to see if it's successful or not. And if the one freeze thaw test is the ASTM C666 test, and a lot of different state DOTs use that test to evaluate their aggregates. Let's see. So I'm getting some more questions. Is it better to place the biggest bars below the smallest bars if I have two rows? So that's a good question. So they just asked about if I have a beam like this, and I'm using 2 layers of bars. I'm stacking my bars because I don't have a large enough thickness to my web. Is it better to use the larger bars at the bottom or the top? Well, I'll tell you, I wouldn't use 2 different size bars. Right? I would try to make it as easy as possible for the people building it in the field, and I would use 1 size bar for everything. You might say, like, whoa, why? What if I could better optimize my design by using 2 size bars instead of 1 size bars? Well, listen, you're not optimizing your design for construction if you use 2 size bars instead of 1 size bars. And really, if people don't build it correctly, it isn't going to be efficient. It isn't going to be effective. We need to make our designs as easy as possible for people to build in the field. And so I would recommend using the same size bar for both. Let's see. Okay, so Jacob just asked a question. When you say the main reinforcement travels between the load path on slabs, what does that mean is what he's asking. And so Jacob, some of this is going to be covered in a video that is going to come out. I think it's on Wednesday morning is when it's scheduled to come out right now on gravity loads, but I'll try to explain a little bit of it right now. So And I'm going to draw a new picture. So Jacob's asking if I have a slab, if I'm going to redraw those T-beams that I was just talking about before, where I have something that looks like this. Awesome. And we got some great questions that we had before about double layers of steel. And we were talking about the T-beam itself. We were talking about the steel that goes here, right? So now we're going to be talking about a different steel. In the slabs go in between the T-beam itself. The slab is actually here. The slab steel is going to traverse in this direction. It's going to go in this direction. Slab steel goes here. Okay, and T-beam steel goes here. So if I was to draw this and go above, put my eye above, let's say my eye is above the system here, eye above, looks something like that. And I was going to look down on everything. So I would have my beams, beam, 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 beam. And in between my T-beam, this area right here is the slab. And so this is where the steel would go for the slab. Steel, 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 steel. The goal of the slab is to get the load to the beams. So this load is actually going to transfer. This load's actually going to go through the slab, and then it's going to get itself to the beam. Through the slab, and then it's going to get itself to the beam. So if I put a point load right here, that point load is going to actually travel through the slab, and that's the steel that I just drew that's going to help it out. And that is going to go down into the beam, and then it's going to travel along the beam length in both directions, along the beam length, until it gets to a column. We haven't talked about columns in class yet, but we will. Don't worry, that's coming. Till it gets to a column. Or if you're using a slab on grade, this is when it gets to the footing, and then it gets itself to the ground. So hopefully that helps a little bit. Kyle says, can use darker color for the steel bars. The beige isn't showing up that well. Sure, man. I appreciate you letting me know. I can use green, and I can do that again. So there's our steel bars here for the slab, longitudinal steel, and then here it would travel on the slab like that. Awesome. Okay, moving on. Gakas asks, what's my thoughts on the update of ACI 31819? I think there's some good changes that they made. And I think they're slowly moving to making it better. I think there'll be even more exciting stuff coming up once they allow some different reinforcing bars to be used. I know they're starting to do that, but I think that is going to be a much bigger focus in the future. And I think we're going to see more changes, allowing more alternative cements to be used as well. So, all right, let's keep going. Let's see. Alex Skin asked, will the videos we watch follow the examples in our notes, or are we done following the notes? No, you should follow the notes. The notes are actually going to be the same thing that are in the videos for the most part. Or at least the essence are going to be the same thing. There's going to be example problems that are going to be straight out of the notes. So your notes are still great. They're still going to be good. So keep using those we've been talking about. Will this video be posted somewhere? I don't know, Brock. I'm gonna try, but I'm not positive. I think so though. And I think it should still be on the channel. Okay, so I'm running out of questions from about slabs and T-beams. So I'm gonna answer a question here about CSA cement. Is using CSA cement better than OPC cement for concrete slab? So that's a great question. So calcium sulfoaluminate cements are very, very powerful cements. They can do some very cool things. They do have some limitations though. It depends what your application is. If you're going to be using them internally for an internal floor slab, I think that there's some really good stuff you can do with them. I think that their shrinkage is going to be a lot less, and I think their curling is going to be a lot less for those slabs. And so I think they can be good. They're more expensive, and not everyone has access to them, but I think they're powerful. If you're going to be using them for external slabs, so slabs that are outside, then I think you have to be a little careful. The pore structure of those cements is very different than Portland cement. That's one reason why it helps it dry so well and not shrink. If you're going to be using it externally, I would be using it with some other additive, some other either a latex additive has been very, very successfully used, or some other additive to try to block the pores. Because if you don't, then outside chemicals will penetrate the concrete readily and could cause you lots and lots of problems. So I've got a paper that's coming out about that that should be published soon. I looked at a review of it over the weekend. So let's see, any other questions? Okay. Any other questions from people here? Another one asked the question, which software do I like better, ANSYS or abacus? So it depends what I'm wanting to do. I've got a lot more experience with abacus, and I think abacus at least used to be more powerful than ANSYS. But I think that, and ANSYS was a little bit more easier to use, but I think it just depends what you're wanting to do. The best of all, in all honesty, is to write your own code in MATLAB. Yeah, write your own finite element code. That way you have ultimate control over what it's doing and how it's doing it, especially if you're doing a nonlinear analysis. And I realize that's not practical for a lot of people, that might not be something that you want to do if you're like a practicing engineer. But if you want to be a researcher, that is the direction that I would go. If you're a practicing engineer, then I think you should use whatever helps you be successful. Let's see, Lucas just asked, hey, are we going to go over shear in these sessions or only the lecture videos? So Lucas, today you're going to get some video, a list of videos to watch that are over shear that are on my channel. We're probably going to have a session that we talk about this, like this, where I answer your questions about shear, and we're going to see kind of how this one went and see what people think about it and go from there. But I'm looking again for more questions that people may have that might be able to help them. Let's see. Mo asked, what is the purpose of AS1 for doubly reinforced beams? So Mo, I think I answered that in the Excel document that I posted on the Dropbox. And it takes a little bit long to answer, but the idea with AS1 in our notes was just to try to balance some of the steel that's in the compression zone with some steel in the tension zone. That helps make the math easier. You can watch the video again. It actually talks about that. And it's just kind of, it's just a trick to make the math a lot easier to do. It helps with the iteration. Hey. Thanks, so Abu Dhabi. I appreciate it. Let's see if there's any more questions people happen to have. All right. Kyle asked, from homework number 2, has a flange of 4 inches. Yeah. No, I did that on purpose, Kyle, because I wanted to try to force you to have a case 2 scenario. But how does this T-beam differ from the 6-inch requirements? It doesn't. It's a made-up academic problem to make you do a case 2, make you do the more complicated problems so you get some practices with that. So that was just done to do that. Awesome. Morgan asks, in case 2 for T-beams, can you thicken the height of the flange when possible to avoid dealing with case 2? Yeah. Yes, Morgan, that's a great question. That what she just asked was, if I have a scenario where I have a T-beam, and for whatever reason, if my zone in tension is large, I'm sorry, my zone in compression is large. In compression is large. Let's say this compression zone goes all the way down here to the bottom, something like this. This whole zone is in compression, 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 right? Is there, she's asking, is there a way that I could get out of being in case two? And she said, could I just make this deeper? And that's one way to do it. But I'll tell you a way that's more efficient is to actually make the entire this distance go down. Okay, it's a lot more efficient to just increase this distance a little bit than it is, and you believe it or not, it will have a huge impact on what your A is for your T-beam. It's much more efficient than increasing this distance, because if you increase this distance, you increase your slab thickness, and your slab thickness is like, it's money, baby. That's where all the money is in a design, is all about the slab thickness. So that's maybe not be the first way that you would want to do it, and the best way you would want to do it. Let's see. So Brian asks, will we receive feedback on our exam 1 or just the grades? You will get feedback, Brian. You will get exam 1. I will scan them all. I will send them to you. Do not worry, but we're still waiting on some folks to take that exam. Kyle asks, when it comes to our good enough method of spending time on design, how much effort should we be spending on serviceability, like long-term deflection versus short-term deflection? Okay, so I think, Kyle, when we always have to do this balancing act of what our designs are all about. And you have to think about what your owner of your structure is going to really, really want. And you need to give it to them. You know, providing value is what I think is the secret to success in life. Providing enough value to a lot of other people is what it's all about. So if you have someone that really values serviceability, like they don't want cracks, they don't want large deflections, then you want to make sure that you give that to them, that you give them a successful slab or structure that does that. A lot of times when it comes to our designs, there's not a lot of people that care as much about serviceability. And so you don't have to focus as much time on those. So you really need to know who your clients are and what they're all about. All right. All right, so we got another question here about, for carbonation purposes, LC3 cement the best option for commercial application goal? That's a great question. I think all of these low carbon footprint cements, all of them, every single one of them has problems with carbonation. I do think, though, that LC3 is intriguing. That's where you mix clay in, an activated clay, or a poor man's activated clay with Portland cement. Also, sometimes fly ash, sometimes slag. I think that's a good thing. But if you don't have the buffering, the high pH from the Portland cement, then I think carbonation is going to be a big problem. I know it is in every other alternative cement that I've ever looked at. And if you don't know what carbonation is, it's where CO2 actually attacks the concrete and starts to lower the pH of it. And once it reaches your rebar, it causes it to corrode and crack. I think it's going to be a huge problem coming up if people aren't concerned or aren't aware of it. Awesome. What else we got here? Let's see. So Julio asked me a question. Have you ever listened about SAP 2000? Do you have any recommendations about the way the last version program solved design problems? I really can't understand how it works. So Julio, I'm not a SAP person. I am a RISA person. RISA 2D, 2D. That's the one that I like. There's 3D out there too, but I'm a fan of RISA 2D. I've studied it pretty heavily. I know how it works. I know what it's about. I know how it does nonlinear problems. and I'm very, very comfortable with it, and that's what I recommend. I have a video on it on my channel that kind of tells people and walks you through a tutorial on how to use it, and I like it better than SAP. I think it's a little simpler than SAP. All right, we got any other questions or preguntas? ¿Cuántas preguntas, por favor? Let's see, I've answered a lot of the questions that people had. Any other questions? I'll tell you what, I have one topic I wanted to cover for people in my class about T-beams, and I got several of these questions over the weekend when the things that I calculated, and on T-beams in general, people asked me why would something about this be effective. That seemed to be something that was kind of confusing to people. That how do you choose what your effective width is for a T-beam and what that's all about. So let's see. So if I have a T-beam in an elevated slab, here's my T-beam, and let's say the distance and finding the B effective is finding what this spacing is. And so this spacing is going to depend on the geometry of my structure. You might say, whoa, it's easy, right? Why are we making this so hard? Why don't we just go halfway between this beam and draw a line, and halfway between this beam and draw a line, and why aren't we done? Why are you making this so hard? Well, because if this spacing, let's say my center to center spacing between the T-beams is something insane, like just crazy. Let's say it's like 100 feet. 100 feet. 100 feet. That's crazy, right? And if we go back, so this when this beam starts to be loaded, if this thing is that large, it is unreasonable to assume that all 100 feet are going to, or 50 feet are going to contribute to the top flange of that beam. It's just not reasonable. It's just not reasonable. And so instead, you have to come up with some distances that are reasonable. And those distances depend a lot on the geometry of the system. So from the notes that we had in class, the three cases that we talked about, hopefully you can somewhat see these. The three cases that we talked about, one of them was half the clear distance between the webs. That's the one that makes sense to everybody. That's the obvious one. One of them is 8 times the height of the flange, and one of them is the length of the span divided by 8, right? The length of the span divided by 8. So the length into the page divided by 8. So any of these can control, and these top two are going to help us when we have these unreasonably large spacings, right? When we have a super large different distances between these webs, that's when these cases help us. And what they do is they help us limit it to what's reasonable. And you might say, why would I ever choose the minimum? I had some questions that people asked that. Why would I ever choose the minimum for this? Well, you have to choose the minimum because you have to choose what's reasonable. And these different dimensions, they're to make us safe, keep us safe. So Kyle asked, for his problem, homework 2 came out to be case number 1. Oh, that's good. And is A less than H of F always case 1? Yeah, that's true. At least if you're using the right A, that's true. So if that's true, Kyle, I'm not saying you're wrong, but if that's true, then I will design another problem and put it on the next homework so that we make sure that we get ourselves a case 2 problem for everyone to have a chance to work. So we've been here a while. We had 73 people on here at once, which is pretty good. I'm just wondering if there are any other questions. We got some other thumbs up coming up. Well, that's always nice for people. Look at that. I think I can hit that or hit that. I don't know. Do we have any other questions on this? Any other questions from anybody that's in the room? Yeah, here's a great one. Do I think the Jedi were to blame for the ultimate demise by banning any close attachments to others? Yeah, I don't know. That's a great question. A very hypothetical question in this very interesting time where we're also trying to keep ourselves away from each other, but yet stay connected through things like social media and things like that. I don't know if I know enough to answer that question, Ridley. I appreciate it, though. Shannon, do you have any questions? Ha. All right. Well, I'll tell you what. I will hang around for a few more minutes to see if anyone's got any questions. If you are an outsider from my class, this would be a great time for you to ask a question because we're kind of following into Star Wars talk right now, which happens in my class sometimes. I'm a big Star Wars freak, and there's some other people are as well in my class, and so there you go. And I just got a comment here about Disney killed Star Wars. I'm not saying that's totally wrong, but you know, if we didn't have Disney making Star Wars movies, we wouldn't have Star Wars to talk about anymore. And I think it could go away, and people wouldn't have anything to discuss. And so at least they're giving us something to discuss. And I'm excited about The Mandalorian, all right? Because I think they've done some really good things there. I'm excited about season 2. I think there's some new actors that are being announced that are going to be in it and some characters coming out. I think it could be really good. Let's see. Dave asked me a question. I've come across a flat slab with drop panels where the bars are rotated 45 degrees to the grid of the columns. Thoughts? Yeah. So Dave is asking me a question about a two-way slab where they've got drop panels. So, and it was an old school concept where you had, this is a column. I'll just draw a drop panel, and we'll just say the column is there. And we'll draw another drop panel, and we'll say the column is there. We'll do the same thing all four around. And students, you know about slabs. We talked about slabs, and we talked about two-way slabs, so you should somewhat understand what we're talking about. So now when you lay steel out in a situation like this, typically the way you would do is you'd put a heavy amount of steel here, 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 and here where the beams are, and you would have a lighter amount of steel in the center. Now, you don't have to do it that way, though. He was saying he had 45 degrees to the grid of the columns. So if this is the grid of the columns, I'm thinking, Dave, you're saying the steel looks something like that. The steel was going in that direction, right? I think that's what you're saying. And the steel may be going in that direction as well. So what you can do to solve that type of problem is you can still work the problem for your slabs in the center, just like you usually would. You can think of your slab as your 1 foot strip, just like you usually would. And when it comes to figuring out how much steel you have in your slab, you're going to not use the total area. You're going to use some component of that. So you might use sine or cosine, depending on what the geometry looks like, to get the component in that direction. And that is going to be what the contribution to the steel would be. So I don't know if that made any sense, but I'll just try to draw it out. If I have my steel going in this direction, what I can do is say I'm not going to be able to count 100% of the area of steel, but I can count some component of that area. So I can break this triangle up into a component, and I can say how much would it be an equivalent amount of steel in that direction, and how much would be an equivalent amount of steel in that direction. And so I can break it up that gives me a reduced effective amount of steel, and that would be one way to design it that way. I hope that made sense. I hope that was right. He's saying yes, and he's saying square grid, so he's not telling me no, so that looks kind of promising. So let's see. Right. So first of all, students, I'm not seeing any other questions from you. So if you need to go, that's fine. I know you have other classes you have to attend online. I'm going to give you a questionnaire about this where you can give me your feedback, what you thought. I am going to stay on and answer a few more questions from other people. You are welcome to stay on and see those questions and see how they go. Again, thank you. I'm sorry for the echo chamber stuff that we had before. I think we got it figured out though, but I will stay on and answer questions to other people if they have them, at least for another 15 or so minutes. So thanks everybody, and look for an email if you're in my class about the shear videos to watch. They're already all online. You can already start watching shear if you want. You could go to the playlist for the reinforced concrete class and go down and just start watching the shear videos, because that's what we're going to end up doing this afternoon. All right, next question. It says, does curing reinforced concrete in salt water leave the steel to greater corrosion? Yes, it does. Curing, any introduction of outside salts during curing, during mixing concrete, at any point in its life, it is going to allow that salt to penetrate down to the rebar, and that is not something that you want to do. I would not recommend that. I don't think that's a very good idea. So Niles said, with stainless steel rebar mixed in an element, would it be a problem for structures and elements that often have cracking all the way through? And in that way, risking a galvanic cell? So I think it could. I think what I know about galvanic cells, and I'm not a guru on them, but what I know about them is that they're a lot worse when they touch. But they also could touch from the pore solution, from the salts and the solution touching between the rebar. I think that's possible, and I think that could cause an issue. I'm not certain that that's been proven to be a problem inside of concrete. I'd want to be able to study that and see if that's an issue. But I see where you're coming from. The simplest solution is just use stainless steel everywhere. That's more expensive. Or a solution that I like, that I'm a big fan of, is to use galvanized steel. If you use galvanized steel, then you protect the steel from any outside chemicals, and it seems to work pretty well. It's kind of like this somewhere in the middle between stainless and typical rebar. I think eventually, when carbon fiber becomes much more prevalent, I think carbon fiber reinforced rebar, I think, is the future. I think it is awesome stuff, and I think it'll be great, but it is crazy expensive. I mean, insanely expensive right now. And you might say, well, why not using basalt rebar? I think that's good too, but I don't think the stiffness is high enough to actually reduce the amount of cracking. So you actually need a lot more steel to keep our cracks small. I talk about that in several videos. You should check it out if you want to learn more about that. Okay, let's keep going. Let's see. So they asked me about mixed designs, and they said the tarantula curve is hard to implement in Europe, and I'd like to learn why you think it's hard to implement there. It's been very successful inside the United States. There's other mixed design procedures that are out there, but I think at the heart of the tarantula curve is what's important. I think if you understand the aggregate gradation that you have versus the aggregate gradation where you start to have problems, then I think that's the secret to getting the aggregates right. Then the next secret is to going after the paste and getting the paste to have the right workability that you want and also the right durability. So it's kind of a balancing act right there. That's when it comes to mix design itself. So that's what I'd recommend. The best book on mix design that I think that's out there is one by a gentleman named Ken Day, who is from Australia, and sadly he passed away about 2 to 3 years ago. The book is dense. The book has lots of different stuff in it, and there's a lot of stuff in the book that I don't agree with. But there is some good things in there and some good mindset in there. And maybe you could ask me some more specific questions so I could try to help you better understand how to apply the tarantula curve for what you're doing where you're at. Hey, Cheater. Thanks for coming back, brother. Hope you're feeling better. So here's a question. They say, hey, what engineering software is worth learning this year? I'll give you my opinion on this. I am not a big fan of software. I'm not a big fan of learning software. I mean, I think software is great. I think it's very powerful. I think it can help you. I'm not saying it needs to go away. I'm not saying not to use it. But what I am saying is that if you spend your time learning how to use software, it's just going to change next year. And it's going to change the year after that. So why not instead spend your time learning about questions or things that you don't know, things that you want to move, things that the whole world doesn't know, things where you can contribute and be special and interesting that other people don't have. So that's where I'd recommend putting your time. How can you be valuable? And if learning software for a certain application is valuable to you, then great, thumbs up. But I think learning to code is better. Learning how to make your own software, learning how to solve your own problems. I think that's a better use of your time. But realize I'm an academic and I solve very strange problems sometimes. And so I have to do that. I think in practice, I think you should use a software that works for you and that is fast and doesn't take too long to do what you want to do. I think that's what it's all about. Hey, Cheater, thank you very much for your tips last night. I appreciate it, and we can see the drawings. Is there any other questions that people have? It says, what do you think of calcium sulfur illuminated cement, CSA cements? So, Dave, I think calcium sulfur illuminated cements are amazing for certain applications. I think they're a game changer. I think they should be used a lot more than they are now. I think they're used for rapid repair techniques now, and I think they can be used for a lot more applications. I think they have a lower carbon footprint. I think they're very, very powerful. I do think you have to understand their limitations. You have to usually use very special mixing equipment with that because they set up and get hard very, very rapidly. You have to have a crew that's trained, that knows what that's all about, that knows how to do that. Now, there are companies out there that sell that are usually pretty good at training and helping people with that, but it just takes a few times to kind of get that right and make sure people kind of understand it. But once you can really hone it in and once you can understand it and get volumetric mixers kind of figured out and get those dialed in, it is powerful. You can do a lot of really, really cool stuff with it, and I would recommend it. Now, one thing to do, watch out. I did talk about this earlier, that you do have to watch out for the permeability of calcium sulfur illuminated cements if they're not used with some other additive, like a polymer, like a latex that fills in the pores, or like some other material that may fill in the pores over time. Some of these companies have figured this out, and they sell products that do that already. And so you should check into that. You should ask questions about that if you care about durability. Now, if you don't, if you are inside or an internal structure or inside, or you're making something else that isn't going to see outside nasty chemicals, then maybe you don't have to worry about that as much. And so maybe that's not as big a deal to you. But I think it's very, very powerful. And I think for whatever application is, you have to see if it kind of makes sense. So there you go. Aha. Cheater says he's a software engineer and he agrees a lot with sentiment a lot. Programs do change and it turns people off, and learning it is a reliable tool to use for the next 20 to 30 years. Yeah, I think that's great. I appreciate you saying that, Cheater. I think that at the heart of what we do, we need to understand the physics of what's going on and be able to really do it and understand it. And then I think the software is a tool to help us do that faster, help us do that more reliably. And there's a video that I shot last night that should get edited and get uploaded soon, where actually I talk about this in a lot more detail. All right, we'll move on to the next one. Oh boy, what a question. How to distribute air that is caused by a PCE plus a defoamer that's less than 2%. Just increase the defoamer or use something different. So I would use a higher, so what this question is, if you're using a polycarboxylate superplasticizer, that there are times when it will actually entrain air inside the concrete when you mix. And if you want that air to go away, then what can you do about it? And a defoamer is the best option. That's the option that I think you should be using. And I would use a defoamer as a normal admixture, and you would have to dial it up or down depending on the concrete that you're trying to produce. If you're doing something that you want non-air entrained, you would go up. If you want air entrained, you're not going to use any. Now, what you'll see over time is actually that PCE dosage, as it changes, goes ups and downs, then it will also affect the defoamer dosage that you need. Also, as the cement characteristics start to change, it'll also change that PCE defoamer. C3A can have a big impact on it. Alkalis can have a big impact on it as well. The slump of your concrete can have a large impact on it. So it's very challenging to get this stuff dialed in. I'd recommend doing a trial batch, dialing in the PCE, and then dialing in the PCE and defoamer for your applications, and then moving ahead. But it is tough. The question was, how much regular non-air entrained concrete should we have? We sell MPAs in concrete here in Ukraine, so maybe as less as we can. So that's a great question. If you're doing external concrete and you want it to last, then you're never going to want to drop below 4% air inside the concrete. That's what I've seen in my research experience. 4% air is the absolute minimum. Now it depends. It's not, air volume is not a good way to assess freeze-thaw durability. You have to really understand the void size distribution, but that's kind of a new concept or new-ish concept that people are putting in inside specifications inside North America, and those are kind of going other places from there. So I guess if you want to get the lowest air content you can possibly get away with, my answer would be 4%, but be careful because not all 4% air contents are created equal. And so you may want to have a little bit more in there just in case something goes wrong. All right, I'm going to take two more questions. I've got this one that's up here. So if you have another question, then you should get it in right now. Placing the bars in that direction, 45 degrees, would help stirrups with shear stress, or it just doesn't affect what system of reinforcement? So I think you're talking about these bars, this 45-degree angle. This was in a two-way slab. So this is in a slab where the load would go two different directions. It would go up and down, and it would go left and right. Now, in a slab like this, you actually don't have stirrups. Stirrups don't exist. You just rely on the thickness of the slab to give it its shear strength. And so you don't need stirrups in it. You use these. So instead, you just use steel. And so the gentleman asked me, could I just use diagonal bars? Or he found a case where he had diagonal bars and he was asking how to analyze it. And so we just said you could still think of it as a strip and just take the component in that direction for that bar. All right. Last question. Oh boy, a great is it possible question. Is it possible to design a triple blended OPC fly ash slag high performance concrete C30 grade concrete for a service life of greater than 100 years for residential high-rise G40 structure? Definitely, not a problem. It's done all the time. You have to understand your concrete mixture. You have to understand what you're wanting to do, but this is something that's extremely possible and very, very, very doable. But now you said something about residential high-rise structure, residential high-rise structure. So when I think of a residential high-rise structure, I don't think of something that needs super long durability, or it's not as far as it doesn't need super low permeability, super low permeability. So I think those are easier to make last a lot longer. And you may not need fly ash and slag to get that design life. It would depend on the environment it's in, what it's doing, what you're doing to it, etc. Now, the one thing I would be concerned about if I wanted to make a 100-year life structure in some situation like that is carbonation. And if you don't know what carbonation is, you should watch my video on YouTube about it. It's got like a dragon and it's kind of fun. But I think carbonation in these high replacement or high amounts of slag, high amounts of fly ash mixtures can be a big deal, because as you reduce the amount of cement in your mixture, you reduce the pH of the concrete, and it reduces the ability for it to protect the steel. And so I think that would be what my one concern. I would want to look at the carbonation rate. If you're at a place that's very, very hot and very, very humid, then carbonation rate could be higher, and you actually might get a longer lasting structure by not using high amounts of slag and fly ash in a residential building, because you don't have the outside exposure. Instead, you would just have the carbonation, the CO2 exposure. I hope that made sense what I just said. You can watch my video and ask me another question if it didn't. All right, last question. Here we go. Thanks, Dave. It says, how do I convince engineers to seriously consider using FRP for the replacement of slabs in parking garages? So Dave, getting people to change is not easy. You have to find a solution that is way better for them, way, way better for them. They have to see lots and lots of benefits to that. So you're going to have to spell out your argument very, very systematically on why you think this is a better solution, what all the benefits it is to them, and all the benefits, everything. You got to lay it all out. You got to talk about money. You got to talk about sustainability. You got to talk about speed of construction. You got to talk about everything. You want to make it as easy for them as you possibly can. And you mentioned the word FRP. I think that one of the biggest challenges with FRP right now is that there's not enough benefit for a lot of applications. I'm not saying all of them. For a lot of applications, enough to convince people to do that. For certain applications, I think it's a no-brainer. If people are tired of replacing things over and over and over and over again, then there you go. I think FRP can be a very good, long-lasting solution. If they're not worried about cracks, all right, and they want something to last a long period of time, then I think that's fine. I think FRP can be fine for that. But I think in some applications, it's more costly and it's tougher to convince people to use it. But that doesn't mean you can't do it. List your benefits out. You've got to be an overwhelming amount of benefit. You got to think about, what's my technique? What's the procedure? What makes most sense to them? And then go back over that over and over and over and over and over again, and just try to help them. And as you try to pitch it to different people, you'll learn about what works and what doesn't work. All right, Cheater, you get the last one, and that's it. Tyler, is concrete being made today something that could last 500 years? 500 years is a long time. Modern concrete, the stuff we're using now, the modern concrete, it's only been around about 120 years, right? 120 years. So I'm not sure how I could say for sure that it will be around for 500. Something could come up that we never ever thought of, never ever anticipated. I talked about carbonation earlier. Carbonation, that's the CO2 penetrating inside the concrete. I would be very, very, very concerned about 500 years and carbonation. Now, with repairs, with tweaks, with other things like that, I think there are definite things that we can do to make our concrete be super long lasting. If you wanted to make concrete last 500 years, you would try to design it without reinforcement. I've got a video about that. It's about why don't we build like the Romans? It talks about arches and domes. If you could build arches and domes in regions where there wasn't fire, there wasn't earthquakes, right? Then I think you could do it. I really think you can, because if you look at the Roman structures that have lasted, the ones that have made it, because a ton aren't around anymore. If you look at the ones that have made it this far, they've made it because they're in mild environments. There's been maybe some earthquakes, but not any major earthquakes, and people have sunk a ton of money into keeping them open and repairing them and making them satisfactory. So if we're willing to do that, then yes, I think modern concretes can last 1,000 years if we do a good job with our steel, if we probably use a minimum amount of steel or do a good job protecting it. Hey, everybody, I really, really appreciate it. Thank you for coming. Take care. This has been awesome. I'm going to be doing this again on Mondays, and we'll see how it goes. As long as there's questions, I'll still try to give you answers. Take care. Bye-bye.